chapter, we are going to concentrate on inequalities. So within the fair game review and then the activities 1 and 2 that you looked at, hopefully you saw that we were dealing with inequalities. So inequalities do compare two quantities. So in the last chapters, we've dealt with equations, two expressions set equal to one another. Well, now instead of being equal, we're going to compare. So in that statement in the first activity, the temperature T has never been below negative 36 degrees Fahrenheit. So what does that mean about that temperature T? If we compare that to negative 36 degrees Fahrenheit, it's never been below that. Has it been that? Yes, or it's been bigger. So that temperature has been greater than or equal to negative 36 degrees Fahrenheit. So to graph that, negative 36, we'll say a little bit more than halfway between negative 30 and negative 40. That or equal to means that negative 36 is included as a possible value, therefore it does get a closed dot. Greater than, what numbers are greater than negative 36? Those numbers occur to that right-hand side, so the right-hand side is what receives that shading. That means any number within that shaded region is a solution to that inequality. 0 degrees. 0 is greater than or equal to negative 36. 30 is greater than or equal to negative 36. Negative 20, also greater than or equal to negative 36. So again, any of the numbers that are covered within that shaded region are solutions. They work in the given inequality. For part B, this time we're told about the elevation is at most. So that elevation E, we're comparing to that 1951.5 feet. At most, that means that's the highest level that can reach. So all other values need to be less than or equal to that 1951.5. Yes, it can equal that. It tells us Tim's Hill is that height. So to graph that, we'll say I'm almost at the 2000. Closed dot because I can use that 1951.5, less than or equal to. So numbers less than or equal to that value come to the left side. So again, any number within that shaded region, 0. 0 is less than or equal to 1951.5. Negative 2000 is less than that. So what we're saying is at most has to be less than or equal to that given value. Well, then in activity 2, you're working backwards. You're given the graph, you want to write an inequality. So you're describing those values of x. Well, we're comparing x, and notice our dot is at 1. It is a closed dot, so it is included as an endpoint, so we would have an or equal to with that. Well, compare the numbers in the shaded region to 1, 2, 3, 4. Those numbers are greater than or equal to 1. So in words to describe that, values, and write it like you would read it. Values greater than or equal to 1. You could say values at least 1. At least also means greater than or equal to. For part B, the only difference between A and B is closed dot versus open dot. Well, that open dot means we're not allowed to use 1 as a solution point. We can use 1.00001. So as long as it's bigger than 1, we're allowed to use it. So take out the or equal to. So that would be values greater than 1. And again, other ways you can say that in terms of an inequality as well. Up to you in terms of how you would write that, as long as it means the same thing. Values more than 1 means the same exact thing. Well, now part C and D the shading's on the opposite side. The open dot, we're still comparing x and 1 in both of these. Closed dot, still have that or equal to. This time our shading comes to the left, therefore x would have to be less than or equal to 1. So we would say values less than or equal to 1. You could say values at most 1. So again, we have different ways of saying that. Is no more than 1. Well, the only difference again between C and D is open dot versus closed dot. We still have values less than 1. We can't use that value of 1. So again, if you see that open dot, that means that particular value is not included as a solution. We are not allowed to use that. 1 isn't less than 1. So an open dot, that endpoint is not included. A closed dot, it is included. So hopefully that gave us a nice review of inequalities. You definitely have dealt with them in the past. So if we then take a look at our notes for today, we start out with a definition of what an inequality actually is. It is a mathematical sentence that, again, compares expressions. So we're not setting expressions equal to one another, we are comparing them to one another. And what kind of symbols are we using? Those 4 inequality symbols. So again, this is not a complete list of ways that you will see this, but it is a pretty good list. The first symbol is less than, probably the most common way. You could also say is fewer than. Next one, greater than. Again, probably the most common way that we see that. Also is more than. So exactly opposite of the less than words. Okay, now we put an or equal to sign under that. So again, that's all that line underneath means, is less than or equal to. Now notice the other 2 as well, is at most. At most, that means we are allowed to include that particular value as a solution, so that does get an or equal to. Is no more than, that means we have to stay less than that value, but again, we can use it. Last one is greater than or equal to. And then again, a few more ways, is at least, which means that's our smallest value. We'd have to use that value or get bigger. Also is no less than. No less would mean greater. No more would be less. So again, just a few of the ways that we will see those inequality symbols referred to in words. It is going to be our job then to use those words to get back to an inequality. So for the first one, it says a number b plus 2.7 is greater than or equal to 3. So pick out your pieces of information. So we have a number b plus 2.7 is greater than or equal to 3. So plus means addition. So b plus 2.7 is greater than or equal to, put in your inequality symbol, 3. That's all we're doing with that, writing it as an inequality. Done. 3 times a number y is at most negative 4. So we have 3 and then times a number y is at most 4. So times means I'm going to multiply, so 3 times y, I'll just show that as 3y, is at most negative 4. If we look back to what we just talked about, is at most, that means that is the highest value we're allowed to reach. So it has to be less than or equal to that negative 4. So again, most of us are going to be good when we see less than, greater than, less than or equal to, greater than or equal to, but keep in mind those other phrases as well. A solution to an inequality is a value that makes the inequality true, just like a solution to an equation. A number that, when plugged in, gives us a true statement. That's the exact same thing for a solution of an inequality. This time, we're going to plug it into an inequality instead of an equation. So we want to know whether negative 2 is a solution. So that's the value for our variable. So they're saying, hey, x is negative 2. Let's see if it works. So if I plug negative 2 in for x, I'd have negative 2 minus 4. Negative 2 minus 4 is negative 6. Is negative 6 less than negative 10? No, it is not. That is a false statement, which means negative 2 is not a solution. True statement, it is a solution. False statement, not a solution. Again, plug in 2 in for our x value, negative 2. So 2.3 times negative 2, we want to know, is that greater than negative 5? So go ahead and simplify then. Take 2.3 and multiply it by negative 2, and you get negative 4.6. Is negative 4.6 greater than negative 5? It sure is. That is a true statement. Therefore, negative 2 is a solution for our second inequality there. So again, when you're asked if something is a solution, plug it in for the variable, simplify, one number on each side, and then make that comparison. That's what an inequality does. If that comparison is true, then that particular value is a solution. If the inequality is false, then the value that you plugged in is not a solution. Graphing, well, realize you already graphed in the activity. You also graphed on the fair game review. So hopefully a review here. So to graph an inequality, a graph is exactly what a graph has always been. It shows all solutions. So it shows every single number that if we were to plug it in would result in a true statement. We use an open dot for less than and greater than, no or equal to. We're not allowed to use that particular value as a solution. So we use an open dot to signify we can get really, really close to that number, but never actually use it as a solution. A closed dot will signify that we are allowed to use that number as one of our values. That has the or equal to. We do shade to show that all the values to that side, either left or right, are solutions. So we have x is greater than 4, no or equal to, open dot, greater than, numbers bigger than 4, shading to the right. Greater than or equal to less than 1, or equal to, I now have a solid dot. Numbers greater than, again, go to the right. X is less than negative 2, no or equal to, so open dot. Numbers less than negative 2, less than, go to the left. X is less than or equal to 3, have the or equal to, so I see my closed dot. Less than, again, my shading goes to the left. Now, one thing I will warn you about, everyone always says, well, I remember that I always shade in the direction that the inequality symbol's pointing. So both of these are pointing to the right, so I shaded to the right. Both of these are shaded or pointing to the left, so I shaded to the left. You have to be careful of that. That only happens when the variable is on the left-hand side. What if I said 4 is greater than x? Well, this also, I can put that on my graph. It still has an open dot. And you say, oh, I'll still shade to the right side. That's the way my arrow's facing. Read it the other way. X is less than 4. 4 is greater than x. Therefore, 4 is the biggest value x can be. This one would have the shading in the opposite direction. Again, if I rearrange and put the variable on the left, My point's pointing at the x, mouth opening towards the 4. So again, the variable has to be on the left-hand side. If you always read the variable first, greater, shade to the right, R in greater, R for right, less than, L left. Have to start with your variable first. So to graph our examples, x is less than 9. So I'll put 0. I'm going to count by 3 so I don't have to count the whole way up to 9 by 1s, which is perfectly fine. Just make sure you label so I know what you're counting by. No or equal to means an open dot. Less than, numbers to the left are less than are 9. X is greater than or equal to 2.5. So I'll go by 1s, which means halfway in between would be my 2.5. I do have an or equal to, which means I do have a closed dot, greater than, shading to the right. Watch the next one. It's flip-flopped of what we would normally have. -1/2 is greater than x. Rewrite it so your variable's on the left. That's where we like it anyway. The point's pointing at our x. So x is less than -1/2. So I'll say -1/2, halfway between 0 and -1. No or equal to, so open dot, x is less than -1/2. So my shading will come to then the left. And our last one, what the heck's going on in there? That is a square root sign. Well, what does a square root sign mean to do? What number times itself equals 25? Another way, what number squared is 25? It is 5. 5 times 5 is 25. So just a little simplification we needed to do there first. Or equal to, solid dot, less than, numbers less than or equal to 5 come to the left-hand side. Watch for some simplification that you may need to do. Be careful, you're not always shading the direction that your arrow faces. Pay attention. If the variable's on the left, that's true. Rearrange it so then the variable is on the left-hand side. Of course, going to finish off with some word problems then. First one, the world record for the largest Pacific blue marlin is 1,376 pounds. M representing the weight of that blue marlin, we want an inequality. So we're comparing M to the 1,376. This is the largest ever caught. So it does actually equal that. So we would have an or equal to. Well, that's the biggest value that's ever been caught. So every other weight would have to be less than or equal to that given value. If it's the smallest, everything else would be bigger. This one's the biggest, so all other weights would have to be smaller than that. For number 2, after 2 games of bowling, Joe has a total score of 475. To win, he needs a total score of 684 or higher. Let X represent the score he needs for his 3rd game to win the tournament. So we want an inequality for X. Well, how are we going to use X, which is going to represent the score he needs in his 3rd game? We have right now a total score of 475. He needs a score of 684 or higher. Well, what does that mean we have to do? Right now, he's at 475. Between where we're at and what he's going to need in his 3rd game, you would need to add those 2 scores together to get to that score of 684. We need to be at 684 or higher. That's the least amount. So that means when we take where he's at now, the 475, and add his third game, that total needs to be greater than or equal to 864. In our next section, we'll look at what we actually would do to find the values of x. For now, though, we're just writing that inequality or possibly even graphing as well.